Hello, everybody. Welcome to Cheenta School of Statistics and Data Science. So, for today, we'll be looking at two questions, mainly probability and probability distribution from the CMI MSC Data Science question paper of 2019, Part B. Okay, so these questions have, like these two questions have uh, an introduction, which kind of introduces some important concepts, which will be used in these two questions. Now, if any of you knows these concepts from beforehand, it helps. But as it is, CMI as an entrance, they kind of provide these information from beforehand to ensure kind of a level playing field. So, all right, so let's dive into this. So we have that, suppose X is a number of successes out of n trials. Okay, so say we have n many trials of something going on. So what is a trial? A trial is basically doing anything that can have a result. And of that, we're counting how many of those results is basically a success, which is denoted by this capital X. Now, capital X is basically like we write this variable in capital letters. This is basically a convention which we use to denote a random variable, which is basically a variable whose value is random. So whether trials are independent, so every trial is independent from the others. The probability of any trial resulting in a success is P. Okay. The probability that there will be exactly k successes out of n trials is probability of x equal to k. Now, this kind of looks like a binomial coefficient. So I'll kind of explain where this comes from in the first place. So say you have got n many slots, kind of, right? Each of those slots can be either success or failure, probability of success being P. Now, these slots are kind of numbered from 1 to n. So I'm told that k of them will be successes. So let's first choose k of these slots, which I can choose by nck. And then I know that all those k slots should have success, that is, which comes with probability P. Since they're independent, I can multiply them. So this will be P to the power k. And the others are all failures, so they come with probability of 1 minus P. And there are basically n minus k slots. And again, they're independent. So I multiply them to get this. N minus k. Okay, now. So that's where this probability comes from, and this k ranges from 0, 1 to n. So the expected number of successes, E of x, is given as NP. This is a formula that we'll be using quite a lot. And here is this small result that we have, that if n tends to infinity, p tends to 0, then this quantity tends to e to the power minus lambda to the power k by k factorial, where lambda is NP. So there's actually another assumption that lambda is equal to NP is constant. So they have not provided this, and it's not really necessary to remember or know this, but like this helps in this case. So n tends to infinity, p tends to 0. This entire product tends to this thing. So the first question is here. Each time a gambler plays a game, there is a 1 in a million chance of winning. The gambler plays the game 1 million times. Find the probability of winning the game 0 times. Right? 0 times. So let's just reference whatever we had here with the information that we have here, right? So just looking at it, there is a 1 in a million chance of winning. This kind of the probability of success, which is kind of 1 10 to the power 6. The gambler plays the game 1 million times. So that gives you the idea that it is n equal to 10 to the power 6. Find the probability of game equal to 0 times. So this is basically k, which is basically 0. So there you have it. And are each of the trials independent? Yes, basically, isn't it? Like a gambler plays a game, right? Like the results of one game shouldn't affect the results of another game that he plays. So they're basically independent. So we can apply this formula that we have here, this very beautiful formula, P of x equal to k. And from there we get P of x equal to 0 is nothing but nc0 into p to the power 0 into 1 minus p whole to the power n minus 0. Simplify this, and this comes out to be 1 minus 1 to the power 10 by 1 minus 1 by 10 to the power 6 whole to the power 10 to the power 6. So this is actually this value. Now in limits, you have done this, right? As n goes to infinity, 1 minus 1 by n whole to the power n should go to 1 by e. Now 10 to the power 6 is a very large value. So this limit, like this thing, will be very close to the limit 1 by e. Now note that like even if you leave the answer at this level, you should get the marks, whatever necessary marks. Like this is icing on the cake. This is 1 by e is not the exact answer. What I'm saying is that this value is very close to this limit, which is 1 by e. So this was the first question. And this is a very simple question. And probably the key takeaway would be just noticing that everything that you would need to solve this question is basically given beforehand. So it's just a question of finding out which variable is what and then applying the formula that they have given in the first place. So it's very simple in that sense. Let's look at the next question, which is given as, suppose x is a random. Actually, I've written this a bit wrong. I copied this wrong. So the question is that suppose x is a continuous random variable which follows a distribution of the probability density function. So it's basically everything is x is a continuous random variable. With probability density function fx is equal to k into x minus x square, where this is called the support of x. That is basically the range of values that x can take. Where k is some constant called a normalizing constant. So we'll see what normalizing constant is later on, not now, honestly. Right. So I have to find the value of k and the expected value of the distribution. So here is a very simple question. I've been given a probability density function, okay, and I have to find some variable, the value of some variable that is in the expression of this PDF. So here we have to use what is called the conditions of when a function can be a PDF. So one of the conditions was this, that we know that if x is a PDF, then the following holds. So this thing holds, right? If you integrate f over all x from minus infinity to plus infinity, you're supposed to get 1. Now this minus infinity and to infinity, this can be actually taken as like this. So minus infinity to 0 fx dx plus 0 to 1 fx dx plus 1 to infinity fx dx. This thing should be 1, right? Now the kind of but how do I say it? The kind of thing that is implied here is that fx takes this value when x is in this range. Anywhere else, it is 0. It's kind of implied, and this probably it would have been helpful if they would have written this in the question. But this you should know that anywhere outside this range, f should be 0. So this value is nothing but 0. This value is nothing but 0. So this entire integral comes out to be 0. This entire integral comes out to be 0. So the only part that gets left is basically this part. So later on, when you will be using the PDFs, you can just take these limits as the upper limit and lower limit of whatever range of values x can take, and this integral will work perfectly. So what we have here is basically 0 to 1 k into x minus x squared dx equal to 1. Take k outside and take also x outside. So this integral, you can remember from your class 11, 12 days that this is a beta integral. This is a beta integral, and we know that, and this is actually of the form that, okay, I'll just write it. Beta integral is to be in this form: x to the power m minus 1 minus x to the power n minus 1 dx used to be gamma n by gamma n plus n, where gamma n is nothing but n minus 1 factorial, if I'm not wrong. So this is the value of this integral. So you can see that m is 2, n is 2. You can see this is basically 2 minus 1, it's 2 minus 1. So the value of this integral turns out to be k into gamma 2 into gamma 2 by gamma 2 plus 2. Just okay, oh, I have written it here already, so you can see this. So simplify this and you should be getting k equal to 6, right? So just get k equal to 6 here directly. Easy calculation. Expectation. So for those of you who are unfamiliar with the formulas of expectation, expectation of a continuous random variable is nothing but this integral. This integral, well, this is over the basically the range, which is again minus infinity. I'll put it like this, but you can then reduce it to 0 to 1 as I have done here in this case. So expectation is 0 to 1 x f x. So let's just take k. K is there already. This also turns out to be another gamma integral, which is again we can put the values in, which is here. Then do the calculation, simplification, comfortably 1 by 2. So this question does require a bit of extra knowledge that probably wasn't that the questions didn't provide, but it shows that knowing the definitions of PDF, what conditions a function must satisfy to be called a PDF, the formulas for expectation and variance for both discrete random variables and continuous random variables. Knowing these things are very helpful, and oftentimes these complicated integrals they reduce to beta integrals, and there's some other cases like reduce to gamma integrals, and you can solve these integrals with properties of definite integrals that we have learned in long ago in class 11, 12. So just brushing up on those formulas, but brushing up on the tricks that you used to use for definite integrals definitely help in solving this. So that would be all for this video. I'll see you later, and thank you.